All right, so in this video here, we'll go over a few, I guess just two sample problems here from the first chapter, which is just on general, introduction to fluid mechanics, but more importantly, some important, introduction to some important fluid properties. And the most important one going forward in our study of fluid mechanics is going to be viscosity and how we relate the strain rate on a fluid parcel or a fluid system, the strain rate within that system to the shear stresses involved, so that then we can relate, the forces. We can look at how the forces affect the system. So the applied forces to a fluid system has on the system. So the first one here is going to be a bit straightforward, and then we'll go to a second one that's a little bit more involved. So let's just start with here. It's problem 1.81 from the book, and I'll show you that. What is written in the book. So here we have a layer of water flowing down an inclined fixed surface with the velocity profile given here, and it's quadratic. So what causes this to be quadratic? Well, if the fixed surface wasn't imparting a shear stress or a force at all, a shear force here to the system, we would just see a uniform profile because there would be nothing else to affect this profile. But we do know that flowing fluids, fluid flow results in shear stresses when it, just in general, I guess in this case. But when we have fluid interacting with a fixed surface, we always get in a theoretical sense, no slip at the wall at fixed surfaces, so the velocity needs to go to zero here, but we know that because this is inclined and it's, the fluid is responding to the gravitational effects, that there will be some flow here. So there needs to be some velocity up at the free surface, but no velocity here at the wall. And it just turns out that, and we'll see this later in the semester probably, that it's a quadratic profile in between. Okay, and the thickness here of the water layer is given. So my rewriting of this problem looks like this, where I've clearly drawn my picture, labeled everything that's important, and put on here the velocity profile. As we'll see later on, we're obviously going to be looking up maybe just one value here, but it could be in general just more values, and we'll make note of them, as you can see right here, as we go along important properties that we've looked up. So the important definition here is the definition of shear stress given a velocity profile. And shear stress is always related to the cross derivative, so it's the of velocity. So it's the velocity in this x direction, but it's derivative in the perpendicular y direction. And that relates here this represents our strain rate, our rate of shear straining to the shear stress involved within the fluid system. But there's a coefficient here, and that tells us how viscous, how much of that, how much does when a fluid strains, the rate of straining, how does that relate to shear stress? And that's related through this coefficient called the viscosity, and that's kind of the important part of, I would say the most important takeaway from chapter 1 in our introduction to fluids. So, as we see here, we can look up in our in the table, and this is just the front cover of the book. Is water here? We're in SI units, so you can see water down here at the bottom. Follow it over to our dynamic viscosity is going to be 1.12 times 10 to the minus 3, and the units are given here, Newton second per meter squared. That's our viscosity of water that we'll need for this problem later on. So I've made note that I looked that up in the table and what the value is, made it very clear on a little side note here. Okay, so the other thing we're going to need, so to get shear stress, we know the viscosity now. We just now need this du dy. Du dy, we look at our velocity profile. This linear term is just going to be 2u over h, 2 big U over h, and then this quadratic term we're going to get 2y over h squared times the big U. So this term, when we take the derivative, still depends on y. This term doesn't. We're looking for the shear stress at the wall, where we've defined y equals 0. So we plug in y equals 0 to our derivative. It's just that this second term just goes away. We're just left with the first term, which is just 2 big U over h. And we're ready to just plug in our values. So the shear stress at the wall is just the viscosity times du dy evaluated at y equals 0. Plug in all of our numbers. This is the table, the lookup value we got from our, for viscosity of water from the table in our book, which is written out here, and then we're just plugging everything in. 2 meters per second is the fixed surface velocity divided by 0.1 meter. It's the thickness of our water layer. And here on these early videos, we'll make sure to be very careful showing how we're dealing with our units, and as a student, you want to be doing that all the time. Maybe later on we won't be as careful as we're going here, but I'm going to stress it here early on. So the units, we have Newton second per meter squared for viscosity, multiplied by a velocity, which is meter per second, and then divided by the thickness of the water, which is another meter. We check here, there's a meter on top, meter on the bottom, those will cancel. Here we have a second on the top and a second on the bottom, those cancel. We're just left with Newton per meter squared. Newton per meter squared, we know, is just force over an area, which is the right units for a stress, and we'll see it's also the units for pressure within a fluid. But for now, so there we're working on our units. At the same time, you're calculating the number, the quantitative value as well. So here we get 0.0448 Newton per meter squared. We can then rewrite the number in scientific notation, 4.48 times 10 to the minus 2. We also have another way to rewrite our units, which is Newton per meter squared is also a Pascal. So here, either one of these, any combination of these would be acceptable here for this answer. I guess that answers the magnitude of the shear stress. It also asks for the direction. And by definition here, and also by common sense, the shear stress of the water on the fixed surface is going to be in the direction of the flow. So, and that should make common sense. Another way you can think about this is that the shear stress of the surface on the water needs to be equal and opposite from our Newton's third law ideas, equal and opposite forces. So the shear stress of the fixed surface on the water needs to be dragging the fluid back. So that needs to be in the opposite the direction of the flow. But the question asks for the direction of the shear stress the water exerts on the fixed surface, which is going to be pulling it, trying to pull it and shear it in the direction of the flow. And so that's just what we've answered here. Shear stress of the water on the surface is in the direction of the flow, and the shear stress of the surface on the water needs to be equal and opposite. So equal in magnitude, opposite in direction. All right. So that we went very carefully through the first problem. Now let's look at a little bit more involved problem, which is problem 1.86 from the book. And let me pull that up from the book. I mean, you can see how I've rewritten it there, but let's take a look at what was originally there. That's here. So we have a pivot bearing used on the shaft of an electrical instrument. So there's an electrical instrument here and a rotating shaft, and a layer of oil here fills the gap between this rotating shaft with a conical, bottom section here and a stationary base. So what we want to know is the frictional torque on the shaft as it rotates with a given rotation rate here. And there's a lot of numbers given in the problem, but here's my rewriting and a little bit simplification of the system. So the question just says determine the frictional torque on a rotating shaft. It's rotating at 5,000 RPM. Its diameter of the shaft is 0.2 inches. The thickness of the oil layer is given as 0.001 inches. This angle, important angle here, is given as 30 degrees, and the oil has a viscosity given there as 0.01 pounds second per feet squared. And that's the system as it was given. Now, how do we go about solving this? Well, torque, we know, is always the accumulation of force over a distance is what is the way to think about this. So the frictional torque in this case for this system is going to be the accumulation of shear stresses that occur over the entire contact area between this rotating shaft and the oil. So it's all the shear stresses right at these at this interface between the rotating shaft and the oil. So little tiny bits of those shear stresses, infinitesimal shear stresses we can call them, multiplied by their radial distance from the rotational axis. So as this thing is rotating about this axis, we need to then multiply by the radius that each of these shear stresses act at. And so it's going to look like this. The total torque is going to be the accumulation over this contact area, right? And making circles out of this conical section. It sweeps in circles. Take the accumulation over this area of the radius times the shear stress over little infinitesimally small bits of area. So the tau dA make up little infinitesimal forces on small elements on this contact surface, and the radius then is the moment arm. So it's the distance from the axis to the rotation, the distance from the axis of rotation to these little elements, dA. All right, so if we then just take a side profile of this system here, here's our rotation axis. We have our rotation rate omega. Here I'm just going to keep things in general, not plug in our numbers until the very end. The radius here, which is going to be our half of our diameter, so it's just going to be 0.1 inches, but right now we're just representing this as a big R, is drawn up at the top, and then we're going to some arbitrary, arbitrary location on this conical section, and labeling that as little r. We then note that our area here, our little infinitesimally small unit, area elements are going to be dA, which is just going to be 2 pi r, so that gives us a circle of radius r, the circumference of a circle, multiplied by little thickness elements, so dl. So that's height along the diagonal here, right? So that gives us the area of small little elements along the area of interest. We then want to be able to relate this to the, we're not given anything about this length here, but we're given an angle, theta is 30 degrees. So we want to relate the radius and the length here to our angle theta. So we look at this, we say, well, we have little, drs, and this will be convenient for integrating in cylindrical coordinates too. So we relate our dl to dr, so little changes in the radius, with our angle. We can do that. So if we redraw the picture here to relate dr to dl, we then have sine theta is dr over dl, and then now we can relate our area is written completely in terms of the radius. We don't have the radius and the length unit along the diagonal. So here we have the area of our infinitesimally small elements is just then 2 pi r dr divided by sine theta. Again, we go to our definition of shear stress, given a velocity profile, so it relates the strain rate and this coefficient of viscosity to our shear stress. And here we assume a linear velocity profile in between, and that's what occurs here. It's a good assumption for an average velocity profile when we have two fixed surfaces rotating and a layer of fluid in between. So we have a linear profile in between that goes from big U, which is given as omega r. Right, so that's just the, given a rotation about an axis, omega r gives us the tangential velocity at some radius away. And this occurs at the shaft to zero velocity out at the stationary base. So u here is our tangential or circumferential velocity that goes into the page here. So this is a little bit, you think about this drawing going into the page. I just wanted to keep the way we look at this the exact same. And then we have our thickness here, t. So we can relate all this. We say that our derivative of velocity, du dy, which is going to go directly into our shear stress definition, is just going to be omega r over t. This is just a linear part, right? So it goes from 0 to omega r over the t. So this is just a change in velocity over the change in this cross direction here. Omega r over t gives us our derivative of velocity across the gap. Okay, we can then now plug everything in. Back to our definition of what our torque is. It's r tau dA. We now have enough to plug in tau, and we have enough to plug in dA. We have our viscosity times our tau, omega r over t. I'm sorry, so this is just completely tau. Right, so this part is tau. There's our r, and then hidden in here, 2 pi r over sine theta is the dA part. All right, so r tau dA. We notice that 2 pi, mu, the omega, the t, the sine theta, those are all constants, and then all we have left inside is just r cubed dr, evaluated from 0 to r. Integrate that, our r cubed goes to r to the 4th over 4. We then have our general formula here for the frictional torque for, for this system here. So the torque, sorry, just refocusing. Our torque is written in this general form. First, we can just look at this and we can, it's nice to keep things in a general form. You don't want to plug in numbers until you absolutely need to. And this is because now we can look at how all of these variables affect the system. How can we increase the friction torque if that's what we're looking for? Or if you're looking to reduce the friction torque, you would ask the opposite question and you'd get opposite answers. But if we're looking to ask how does the friction torque get increased? Well, you could increase the viscosity. Well, that makes common sense. You could increase the rotation rate. Well, that makes sense. That's going to create more torque on the rotating shaft. We could decrease the thickness, make it a thinner gap. We could decrease this angle, okay, so make it more vertical. But the big thing, right, so this goes as r to the 4th. Everything else here was had a power of 1. The radius here goes r to the 4th. So really, that's going to be the big player here. As if we increase this radius, basically making the system bigger. So if we don't change anything else but change big R, we're essentially making this region of the shaft that has, that interacts with the gap of the oil, that has that shear straps acting over a bigger surface, and also that surface is going to be farther away from our rotation axis, which is going to produce a bigger torque. All right, so for both of those reasons, not only does R responsible for a larger area, but it's also going to put more of that shear stress at a further location from the axis of rotation, thus greatly increasing the frictional torque. We plug everything in, again, being very careful with our units. The only one I'm going to point out here is our rotation rate, which is given in RPMs. We need to translate that, it's revolutions per minute. We need to translate that into radians per second, and that gets multiplied by 1 minute over 60 seconds to convert the minute to second, and then multiply 2 pi radians per revolution to go from revolutions to radians. We're left here plugging everything in. We noticed that our viscosity was given in feet, and I'm interested in working in, and then the other ones are written in inches, and I'm interested in working in feet here. So be careful here. This radius here is 0.1 inches to the 4th. If we're going to convert this to working in feet, we then need to multiply by 1 over 12 to the 4th power. So you need to have 4 of those, and on the bottom we're just going to have 1 of those. So in the end you're multiplying this whole system by 3 of these factors to get to this final answer. It's 9.5. Well, here, another thing I want to be careful with here. If you just plug this into a calculator, you might get something like 9.5193, more and more significant, or decimal places, values later on in our decimals, and that's beyond the level of accuracy for our calculations. Noting what the level that was given to us in the givens. So the way we answer this here, it's pretty typical, and we went through this in the introductory video, but this is just 9.52. Keep 3 significant figures, unless out front is just a 1, then you might want to keep more. So 3 or 4 significant figures, and that should satisfy. So the final answer here is the frictional torque is 9.52 times 10 to the minus 4 feet-pounds. Okay, so that's the end of this video. Going over a couple problems looking at what viscosity is and how it relates strain rate to shear stress, and we'll see that this is going to come up throughout the rest of our study of fluid mechanics.